Tonight, we're exploring one of the strangest mysteries in Earth's history: how a dead volcanic world with toxic skies somehow became a planet humans could breathe on. From endless ancient storms to the rise of oxygen and the invisible shield protecting life today, this is the incredible story of Earth's atmosphere. Before we begin, leave a comment below telling me where you're watching from tonight. And do you think a planet like Earth is rare in the universe? More than 4 billion years ago, Earth would have looked nothing like the world outside your window tonight. There were no blue skies drifting over oceans, no forests moving with the wind, no oxygen filling the air with the quiet promise that breathing would continue without thought. 2. If you had somehow stood on the surface of the young Earth during those first violent ages, the planet would not have welcomed you as home. It would have tried to erase you almost instantly. The ground itself was barely solid. Entire regions glowed red beneath oceans of magma, while massive cracks in the crust leaked rivers of molten rock across the surface. The sky above was not truly a sky in the modern sense, but a suffocating haze of ash, vapor, toxic gases, and burning debris left over from the birth of the solar system. Everywhere, things were still colliding. Asteroids and protoplanets smashed into Earth with enough force to boil oceans before oceans even fully existed. Some impacts were so powerful they may have briefly turned huge portions of the planet back into liquid stone. And strangely, despite all that chaos, scientists believe this was still the beginning of the atmosphere you are breathing right now. When Earth first formed around 4.5 billion years ago, it emerged from a rotating cloud of dust and gas surrounding the young sun. Tiny grains collided and stuck together, gradually building larger and larger bodies through gravity. Over millions of years, one growing mass became large enough to dominate its region of space. That mass would become Earth. But early Earth was less like a finished planet and more like a construction site inside a cosmic war zone. Temperatures were extreme. Radioactive decay heated the interior from within, while constant impacts heated the surface from above. One collision in particular may have changed everything forever. Many researchers believe a Mars-sized object, often called Theia, slammed into the young Earth during its earliest history. The impact was catastrophic enough to blast enormous amounts of material into orbit, material that would later form the Moon. But the collision may also have stripped away much of Earth's earliest atmosphere. That first atmosphere was probably thin and short-lived anyway. In the earliest stages, Earth likely captured lightweight gases drifting through the solar system, mainly hydrogen and helium. The same basic ingredients found in the Sun and giant planets like Jupiter. But Earth was too small and too warm to hold on to them for long. Solar radiation and violent impacts gradually swept those gases away into space. In a way, Earth failed its first attempt at becoming a livable world. And this raises a strange possibility. A planet can exist without an atmosphere much more easily than life can. Look at the Moon. It has gravity, rock, mountains, ancient lava plains, but almost no real atmosphere. Mars once had rivers and thicker air, yet much of it disappeared over time. Venus went in the opposite direction, trapping heat beneath a crushing atmosphere thick with carbon dioxide until the surface became hot enough to melt lead. Earth somehow avoided both fates, but at the time, there was no obvious reason it should have. One of the most unsettling things about the early Earth is how unstable everything was. Even after the surface began cooling, the planet remained under constant attack from space debris left over from planetary formation. Some scientists refer to part of this era as the late heavy bombardment, a period when impacts became extraordinarily frequent. The exact timing and severity are still debated, but evidence from lunar craters suggests that enormous collisions shaped the inner solar system for hundreds of millions of years. Imagine trying to build an atmosphere while giant rocks from space keep detonating across the planet. Each impact carried enormous energy. Some collisions vaporized rock instantly. Others may have temporarily heated parts of the atmosphere enough for gases to escape Earth's gravity entirely. The young planet was caught in a cycle of destruction and rebuilding over and over again. Yet slowly, almost invisibly at first, Earth began changing. The turning point may have come not from above, but from deep below the surface. Inside the planet, heat continued building. Heavy elements like iron sank toward the center while lighter materials rose upward, creating layers inside Earth's interior. This process released staggering amounts of trapped energy. Volcanoes began erupting on a scale almost impossible to imagine today. Entire regions of the planet cracked open. Lava flooded outward continuously. But these eruptions were doing something even more important than reshaping the surface. They were releasing gases, water vapor, carbon dioxide, nitrogen, sulfur compounds, toxic chemicals, invisible clouds rising from the interior of the Earth itself. In other words, the planet was beginning to breathe. Modern scientists often describe this process as outgassing, the release of gases trapped within molten rock deep underground. Over immense stretches of time, volcanic eruptions pumped huge amounts of material into the atmosphere. Some researchers believe most of Earth's modern atmosphere ultimately came from this process. The air surrounding the planet today may have once been locked inside minerals, buried beneath ancient oceans of magma. But this new atmosphere would have been horrifying by modern system standards. There was little or no oxygen. Instead, the air may have been dominated by carbon dioxide, methane, ammonia, sulfur dioxide, and dense steam. The smell alone would likely have been unbearable. Some models suggest the sky itself may have appeared orange, dark red, or brownish beneath thick volcanic haze. Sunlight would have struggled to fully penetrate the atmosphere. Lightning storms may have raged constantly through dense clouds of ash and vapor. And yet, without this terrifying atmosphere, life might never have appeared. That contradiction sits at the center of Earth's story. The same gases that would kill most modern organisms were probably essential for making the planet habitable in the first place. Carbon dioxide and methane trapped heat through a greenhouse effect, preventing the young Earth from freezing completely. This mattered because the sun itself was weaker billions of years ago. According to current models, the early sun produced significantly less energy than it does today. By simple calculations, Earth should have been frozen solid. Oceans should have remained locked beneath global ice. But geological evidence suggests liquid water existed surprisingly early. This mystery is sometimes called the faint young sun paradox. Somehow, despite receiving less solar energy, Earth stayed warm enough for water to remain liquid. One possible explanation is that greenhouse gases in the ancient atmosphere were far more abundant than they are today, trapping enough heat to stabilize temperatures. But scientists still debate exactly which gases dominated and how stable the climate truly was. The deeper researchers look into the ancient atmosphere, the stranger the picture becomes. Some hypotheses suggest thick methane hazes may have covered the planet like a veil, similar to Saturn's moon Titan today. Others propose that gigantic volcanic eruptions continuously recycled gases into the atmosphere faster than impacts, or chemical reactions could remove them. There are even debates over when Earth first developed permanent oceans and whether parts of the surface repeatedly boiled away before stabilizing. In many ways, the atmosphere was not a finished system yet. It was still evolving alongside the planet itself. And perhaps the most fascinating part is that none of this was guaranteed to succeed. Earth existed in a narrow balance between disaster and stability. Too little atmosphere, and the planet could have become a frozen wasteland like Mars. Too much carbon dioxide, and Earth might have spiraled into a runaway greenhouse state like Venus. Even the planet's size mattered. Gravity needed to be strong enough to hold gases close, but temperatures needed to cool enough for water vapor to condense. Small differences early on might have changed everything. If Earth had formed slightly closer to the Sun, the oceans may never have survived. Slightly farther away, they may have frozen permanently. If the moon-forming impact had been stronger, perhaps the atmosphere would have been lost entirely. If volcanic activity had weakened too early, the planet may never have rebuilt its air. Sometimes, the history of Earth sounds less like a stable design and more like a long sequence of near misses, and still one enormous problem remained unsolved. Even after volcanic gases filled the sky, even after temperatures stabilized enough for liquid water to exist, Earth was still not breathable. There was no oxygen-rich atmosphere waiting for future animals or humans. The air remained toxic, heavy, alien. The world had oceans now, storms now, clouds now, but not the kind of atmosphere complex life would eventually need. At some point, something would have to transform the entire planet, not through explosions, not through impacts from space, but through living organisms so small that the naked eye would never notice them. Because the next chapter of Earth's atmosphere would not be written by volcanoes or asteroids. It would be written by life itself. There was a time when the surface of Earth may have looked less like a planet and more like the inside of an endless furnace. Vast oceans of molten rock stretched across entire continents that did not yet fully exist, glowing beneath a dark atmosphere thick with ash and chemical haze. The ground split open constantly. Lava surged through cracks, hundreds of miles long. Entire regions of the young planet rose and collapsed under pressures almost impossible to imagine today. And from those wounds in the crust, something invisible began pouring into the sky. Not life, not oxygen, but the raw ingredients that would eventually make breathing possible. In a strange way, the first real atmosphere of Earth may have been exhaled directly from the planet's interior. Modern volcanoes already release enormous amounts of gas during eruptions, but the volcanoes of the early Earth operated on a completely different scale. Many scientists believe the young planet was still releasing leftover heat from its violent formation, while radioactive elements deep underground added even more energy into the interior. The crust was thinner, weaker, and far less stable than it is now. Instead of isolated eruptions separated by decades or centuries, volcanic activity may have been nearly continuous across large portions of the globe. Some researchers suspect entire oceans of magma persisted for millions of years after major impacts. Others argue the surface may have cooled faster in certain regions, creating temporary crusts that repeatedly melted again under bombardment and internal heat. But regardless of the exact timeline, one thing appears increasingly clear. Earth's atmosphere was not simply captured from space. Much of it was manufactured from below. Deep inside molten rock, gases were trapped under extreme pressure: water vapor, carbon dioxide, nitrogen, sulfur dioxide, hydrogen sulfide, methane. As magma rose toward the surface, pressure decreased, allowing these gases to escape violently into the air. The process is sometimes compared to opening a shaken bottle of soda, except on a planetary scale. Every eruption added more material into the atmosphere. To over immense stretches of time, the sky itself slowly thickened. It is difficult to picture just how alien this world would have appeared. There was no blue horizon, no breathable air, no quiet weather patterns moving gently across oceans. The atmosphere may have been so dense with volcanic particles that sunlight struggled to fully penetrate the haze. Some models suggest the sky may have carried deep orange or reddish tones caused by suspended chemicals and scattered light. Lightning storms may have flashed constantly through clouds rich in ash and steam. Sulfur compounds likely gave the atmosphere a toxic smell similar to volcanic vents today, but magnified across the entire planet. In some regions, rain may have fallen hot enough to scald exposed rock. And yet, this violent environment was slowly solving one of Earth's greatest problems. It was creating stability. Earlier in Earth's history, lightweight gases like hydrogen and helium had largely escaped into space. The planet needed a heavier atmosphere capable of surviving long-term. Volcanic axes provided exactly that. Nitrogen, in particular, would become one of the most important components of Earth's future atmosphere. Even today, nitrogen makes up nearly 78% of the air you breathe, yet most people rarely think about it because oxygen receives all the attention. But oxygen alone would not create a stable atmosphere. Nitrogen acts almost like a silent structural framework, moderating pressure and diluting reactive gases that might otherwise make the atmosphere dangerously unstable. The strange part is that while volcanoes were helping Earth become habitable, they were also making the surface extraordinarily hostile at the same time. Carbon dioxide concentrations may have been hundreds of times higher than modern levels. Sulfur gases mixed with water vapor to create acidic rainfall. Methane trapped heat efficiently, possibly warming the planet despite the weaker young sun. Some scientists suspect the greenhouse effect on early Earth was absolutely essential. Without it, the planet may have frozen solid. This remains one of the biggest puzzles in planetary science. Billions of years ago, the sun emitted significantly less energy than it does today, perhaps around 70% of its current brightness. By basic physics, Earth should have been covered in global ice. Yet ancient minerals suggest liquid water existed surprisingly early. Something was compensating for the weaker sunlight. Greenhouse gases remain one of the strongest explanations. Carbon dioxide likely played a major role, though methane may have contributed even more than once believed. Certain researchers propose that methane-producing microbes appeared early enough to intensify warming further, though the timing is still debated. Other scientists argue volcanic carbon dioxide alone may have been sufficient under the right atmospheric pressures. The deeper scientists investigate ancient climate systems, the more it becomes clear that Earth's survival may have depended on a remarkably delicate balance between heating and cooling forces. Too little greenhouse warming and the oceans freeze. Too much and Earth risks becoming another Venus. Venus serves as a haunting reminder of how differently this story could have ended. Today, its atmosphere is overwhelmingly carbon dioxide, with surface temperatures hot enough to melt lead. Some planetary scientists believe Venus may once have possessed oceans, billions of years ago before a runaway greenhouse effect transformed the planet permanently. The comparison unsettles researchers because early Earth and early Venus may have started with surprisingly similar ingredients. Yet one world stabilized while the other became an inferno. Even now, scientists still debate exactly why. One possibility involves distance from the Sun. Venus receives significantly more solar energy, which may have prevented long-term cooling and allowed water vapor to accumulate in the atmosphere. Since water vapor itself is a powerful greenhouse gas, the heating may have accelerated uncontrollably. To Earth, meanwhile, occupied a narrower zone where liquid water could eventually condense and begin removing carbon dioxide from the atmosphere. But this transition may not have happened smoothly. Some theories suggest early Earth experienced periods of extreme instability before settling into more stable climate cycles. Gigantic eruptions may have temporarily darkened the atmosphere while simultaneously releasing warming gases. Massive impacts may have boiled parts of the oceans repeatedly. In some models, entire regions of the surface alternated between cooling crust and renewed magma seas. Over and over again, Earth was not peacefully evolving toward life. It was struggling violently toward equilibrium. Water vapor played a particularly important role in this transformation. Volcanoes released enormous quantities of steam into the atmosphere. As temperatures gradually cooled, some of that vapor condensed into clouds. Then came rain. Not ordinary rainstorms lasting hours or days, but potentially rainfall on a planetary scale lasting thousands or even millions of years. Some researchers believe the first oceans formed gradually as water condensed from the atmosphere itself, collecting in low regions of the crust as the surface cooled enough to hold liquid water permanently. Other scientists suggest additional water arrived from icy asteroids or comet impacts during the solar system's chaotic early era. Evidence exists for both possibilities, and many researchers suspect the answer may involve a combination of internal volcanic release and extraterrestrial delivery. What matters is that once stable oceans appeared, Earth changed fundamentally. Water began interacting chemically with the atmosphere and surface rocks. Carbon dioxide dissolved into the oceans. Minerals trapped certain gases permanently. Climate systems slowly became more complex. In a sense, Earth had begun regulating itself. This idea fascinates scientists because the planet almost behaves like a giant feedback system. Volcanoes release carbon dioxide. Rain removes some of it through chemical weathering. Oceans absorb gases. Tectonic activity later recycles material back into the mantle. Over immense periods of time, these processes may have helped stabilize temperatures enough for life to survive. But there is still debate over how stable early Earth truly was. Some evidence hints at catastrophic swings in climate and atmospheric chemistry that nearly pushed the planet toward frozen or overheated states multiple times. The farther back researchers look, the less certain the picture becomes. Even the color of the sky remains uncertain. Depending on atmospheric composition, haze thickness, and solar radiation, the early atmosphere may have looked dark orange, copper-colored, pinkish, or even brown under certain conditions. Sunsets may have appeared permanently apocalyptic. Dense methane haze could have scattered light in ways modern humans have never witnessed naturally on Earth. If you stood there, assuming you could survive somehow, the planet might have felt less like home and more like a distant alien world orbiting another star. And still, beneath all the violence, something extraordinary was happening. The atmosphere was growing thicker, oceans were stabilizing, temperatures were moderating enough for chemistry to become increasingly complicated. Earth was no longer merely a molten rock drifting through space. It was becoming an active world with cycles, weather, pressure systems, and chemical interactions unfolding continuously across the surface. Yet, despite all this progress, the atmosphere remained deadly by modern standards. There was still almost no free oxygen. Any human transported into that world would suffocate quickly, even if the heat and toxic gases did not kill them first. In fact, oxygen may have been nearly absent, precisely because Earth had not yet encountered the force that would transform everything forever. Because volcanoes could build an atmosphere, but they could not create the kind of atmosphere complex life would eventually need. That transformation required something smaller than mountains, quieter than eruptions, and far more dangerous to the ancient world than any asteroid from space. It required the arrival of organism capable of changing the chemistry of an entire planet. There may have been a time when rain fell on Earth for so long that the planet itself disappeared beneath it. Not storms lasting days or seasons, but rainfall continuing across unimaginable stretches of time while the young world slowly transformed from a volcanic wasteland into something entirely different. The sky would have been almost unrecognizable compared to modern Earth. Thick clouds covered the atmosphere from horizon to horizon, illuminated faintly by a dimmer young sun, struggling to penetrate layers of steam, ash, and chemical haze. Lightning flashed endlessly through the darkness. Volcanoes continued erupting across the surface, releasing more vapor into the air, even as the planet desperately tried to cool. And somewhere, during this violent chapter of Earth's history, the first true oceans began to appear. It sounds almost impossible that something as calm and familiar as rain could emerge from such chaos. Yet water may have become the single most important force in shaping the atmosphere and future of the planet. Before the ocean existed, Earth was trapped inside a very different balance. Volcanoes had already filled the atmosphere with enormous amounts of water vapor, carbon dioxide, nitrogen, methane, and sulfur compounds. The air was thick, hot, and toxic. Surface temperatures in many regions may have remained high enough to keep water suspended as steam instead of liquid. But slowly, over immense spans of time, the planet radiated heat into space. Crust thickened. Conditions stabilized just enough for something extraordinary to happen. Water in the atmosphere began condensing faster than it evaporated. Clouds thickened further. Then came rain on a scale no human has ever witnessed. Some scientists believe the cooling process may have triggered periods of nearly continuous global rainfall, lasting thousands or even millions of years. It is difficult to visualize that amount of water moving through the atmosphere, entire skies collapsing endlessly onto the surface, steam turning into oceans one drop at a time. lava plains hissing beneath boiling rainstorms, rivers carving into newly formed crust before the crust itself melted again under volcanic heat. Earth was not yet peaceful. It was still unstable, violent, and dangerous, but the arrival of liquid water changed the rules of the planet completely. Water is strange, even by cosmic standards. Most substances become denser as they freeze, but water expands into ice. It dissolves chemicals exceptionally well. It absorbs and stores heat efficiently. It moves constantly between vapor, liquid, and solid states. Because of these properties, once stable water appeared on Earth, the atmosphere and surface became locked into an increasingly complex relationship. Rain began pulling carbon dioxide from the atmosphere. Oceans absorbed gases directly. Minerals dissolved into water and reacted chemically with the crust. For the first time, Earth started behaving less like a raw, molten planet and more like an interconnected system. Some researchers believe this transition may have saved Earth from becoming another Venus. Venus today remains wrapped beneath an atmosphere so dense and hot that liquid water cannot survive on the surface. But on Earth, once temperatures cooled enough for rainfall and oceans to persist, water began removing large amounts of carbon dioxide from the air through weathering and ocean absorption. Carbon became trapped in rocks, sediments, and eventually the seafloor itself. In a sense, the oceans may have acted like giant planetary regulators, slowly preventing greenhouse gases from spiraling completely out of control. But this process was probably far messier than it sounds. Ancient Earth likely swung between extremes repeatedly. Some models suggest portions of the surface may have boiled while others cooled. Massive asteroid impacts could have temporarily vaporized sections of the oceans before rainfall rebuilt them again. Gigantic eruptions may have darkened the atmosphere for centuries while simultaneously seizing even more greenhouse gases. The planet was balancing on the edge between freezing and overheating for immense stretches of time. And somehow it never fully crossed either line. One of the biggest mysteries surrounding Earth's oceans is where all the water actually came from. Volcanoes certainly released enormous amounts of steam from Earth's interior, and many scientists believe much of the planet's water originated there. Yet another possibility comes from space itself. During the early solar system, countless icy bodies drifted through the inner planets. Some researchers argue that asteroids rich in water-bearing minerals slammed into Earth repeatedly, gradually delivering additional water over hundreds of millions of years. Comets were once considered likely candidates too, because of their enormous ice content, though later, chemical studies complicated that idea. Scientists often compare hydrogen isotopes inside Earth oceans with those found in comets and meteorites to trace the source of the water. The results remain debated. Some evidence points more strongly towards certain types of asteroids. Other studies suggest Earth may already have contained significant water deep inside its mantle from the very beginning. The answer may ultimately involve several sources working together, and perhaps that uncertainty makes the story even more fascinating. Every ocean wave on Earth today may carry traces of both volcanic fire and ancient collisions from deep space. Once stable oceans existed, the atmosphere began changing in ways that reached far beyond climate alone. Water cycles created weather patterns. Evaporation and rainfall moved heat around the planet. Clouds reflected sunlight, while also trapping warmth. The interaction between oceans and atmosphere became one of the defining systems shaping Earth's future. Even now, billions of years later, the climate remains deeply connected to the movement of water through air and sea. Yet the early oceans themselves may not have resembled modern oceans very closely. Scientists suspect they were chemically different, likely richer in dissolved iron and other volcanic materials. The water may have appeared greenish, dark, or murky beneath a thick atmosphere filtering sunlight differently than today. Without oxygen in the atmosphere, many chemical reactions behaved in unfamiliar ways. Ultraviolet radiation from the sun penetrated the surface more aggressively because no ozone layer existed yet. Some researchers believe shallow coastal environments repeatedly evaporated and refilled, concentrating chemicals that may later have contributed to the origin of life itself. This possibility has become one of the most intriguing ideas in science. Water did not merely make Earth habitable, it may have helped create the first living systems. No one knows exactly how life began. The evidence from that era is frustratingly incomplete, because Earth's surface has been recycled constantly through tectonic activity, erosion, and volcanic processes. Most rocks from the earliest chapter of Earth's history no longer exist, but many scientists suspect water played a central role. Some hypotheses focus on deep-sea hydrothermal vents where mineral-rich hot water mixed with colder oceans, creating chemical gradients that primitive life could exploit. Others point toward shallow tidal pools exposed to cycles of evaporation and concentration. Certain researchers even propose that lightning storms inside the early atmosphere helped form organic molecules that later accumulated in water. None of these explanations are universally accepted, and perhaps several environments contributed simultaneously. But nearly every major theory of life's origin shares one common ingredient: liquid water. Without oceans, Earth might have remained geologically active, yet biologically empty forever. And still, despite the arrival of seas, clouds, rainfall, and more stable temperatures, the atmosphere remained deeply alien. There was still almost no free oxygen. If anything, the oceans themselves may have delayed oxygen's rise by absorbing chemicals that reacted with it immediately. Iron dissolved in seawater captured oxygen as fast as primitive organisms could eventually produce it. The atmosphere stayed dominated by gases that modern humans would consider toxic. Methane may have played a particularly important role during this era. Some researchers suspect methane concentrations were dramatically higher than today, helping warm the planet under the weaker young sun. Certain models even suggest methane haze could have formed global layers high in the atmosphere, tinting the sky and affecting climate in ways difficult to fully reconstruct now. Under some conditions, the young Earth may have looked eerily similar to Titan, Saturn's massive moon, with thick hazy skies filtering sunlight into a dim orange glow. Yet unlike Titan, Earth possessed something far more unstable and powerful: liquid water moving endlessly across the surface. The oceans also introduced a new kind of memory into the planet's systems. Rocks recorded chemical signatures, sediments trapped traces of ancient atmospheres. Minerals preserved clues about temperatures, volcanic activity, and ocean chemistry. Billions of years later, scientists still study these microscopic signals to reconstruct a world no human ever saw. Tiny isotope ratios hidden inside ancient zircon crystals suggest liquid water may have existed astonishingly early, perhaps within only a few 100 million years after Earth formed. If true, that means the transition from molten chaos to ocean world may have happened faster than scientists once believed. And that realization changes the entire story of habitability. It suggests planets might stabilize sooner than expected under the right conditions. Or perhaps Earth was extraordinarily lucky. The truth is that no one knows how common worlds like this really are. Astronomers now discover exoplanets constantly, some rocky, some potentially Earth-sized, some orbiting inside regions where liquid water might exist. But detecting oceans directly remains incredibly difficult. A planet with water may still become uninhabitable if its atmosphere evolves differently. Earth's history reveals how fragile these balances truly are. Oceans alone are not enough. Atmosphere alone is not enough. Temperature, pressure, chemistry, volcanic activity, magnetic protection, solar radiation, all of it interacts together. Remove one piece, and the story may end very differently. And somewhere within those endless ancient storms, while rain hammered volcanic rock and the first oceans spread across the cooling surface, another invisible transformation was quietly approaching. Because the atmosphere of Earth possessed at this stage could support water, weather, and perhaps primitive chemistry, but it still could not support complex life. The sky remained toxic. The oceans remained chemically hostile. The air itself carried almost none of the oxygen modern creatures depend upon. Yet, hidden within those dark waters, life may already have been preparing to change the entire planet forever. If you could stand on the shoreline of Earth more than 3 billion years ago, the planet might appear strangely alive and completely dead at the same time. Oceans already stretched across much of the surface, storms moved through a thick atmosphere, volcanoes glowed along distant horizons, and chemical reactions unfolded endlessly beneath dark waters. Yet, despite all this activity, the world still lacked the one thing modern humans instinctively associate with life itself. There was almost no oxygen in the air. Not just less oxygen than today, but so little that a human being transported there would lose consciousness within moments. The strangest part is that this was not considered a problem by the life forms already living on Earth. In fact, for many of them, oxygen would have been poison. Modern humans think of oxygen as the very definition of survival because every breath we take depends on it. But for nearly half of Earth's history, life existed without using oxygen at all. The earliest organisms evolved in a world where entirely different chemistry ruled the planet. The atmosphere was still dominated by gases like nitrogen, carbon dioxide, methane, and water vapor. The oceans themselves carried the dissolved minerals and metals in concentrations unlike anything found today. Under those conditions, the first life forms adapted to a planet that modern creatures would barely recognize. Scientists still debate exactly when life first appeared. Some evidence suggests microbial life may have existed astonishingly early, perhaps more than 3.5 billion years ago, not long after the oceans stabilized. Tiny fossil-like structures preserved inside ancient rocks hint at microbial communities living in shallow seas. Chemical signatures trapped in carbon-rich minerals also suggest biological activity may have emerged surprisingly quickly once liquid water became stable. Yet almost everything about this era remains difficult to reconstruct because Earth has recycled so much of its own surface through tectonic activity, erosion, and volcanism. the oldest evidence survives only in fragments. Still, even those fragments reveal something extraordinary. Life began on a planet with no breathable atmosphere. The earliest organisms likely belong to a category scientists call anaerobes, meaning they survived without oxygen. Some generated energy through chemical reactions involving sulfur, iron, hydrogen, or methane instead. Others may have thrived near hydrothermal vents deep beneath the oceans where hot mineral-rich water poured from cracks in the seafloor. In those environments, darkness dominated completely. No sunlight reached the depths. Yet chemical energy flowing from Earth's interior created pockets where primitive ecosystems may have survived. Certain modern microbes living near deep-sea vents today are sometimes viewed as distant echoes of those ancient worlds. They survive in conditions once thought impossible for life. Superheated water, crushing pressure, toxic chemicals, complete darkness, and somehow they endure. This possibility changes the way scientists think about habitability itself. Earth may not have required calm, paradise-like conditions for life to begin. In some theories, instability and chemical violence may actually have been essential ingredients. The young planet offered endless energy sources: volcanic heat, lightning, ultraviolet radiation, impacts from space, and mineral-rich oceans constantly mixing together. Instead of preventing life, that chaos may have accelerated the chemistry needed for biological systems to emerge. Yet, the atmosphere remained deeply alien. Methane may have played a major role in shaping climate during this era. Certain ancient microbes possibly released methane into the atmosphere as a byproduct of their metabolism, gradually contributing to greenhouse warming. Some scientists suspect methane concentrations became so high that the sky itself may have developed a hazy orange tint similar to Saturn's moon Titan. Under such conditions, sunlight reaching the surface would have looked dimmer and more filtered than today. Oceans may have reflected copper, green, or dark gray tones beneath thick atmospheric haze. It was a living world, but not a familiar one. One of the strangest differences involved the oceans themselves. Today, Earth's oceans contain oxygen dissolved in the water, supporting fish, whales, and countless marine ecosystems. But billions of years ago, oxygen was almost entirely absent from the seas as well. Instead, ancient oceans contained enormous amounts of dissolved iron released from volcanic activity and underwater hydrothermal systems. Without oxygen present, iron remained suspended in seawater rather than rusting and sinking. Entire oceans may have carried a dark greenish color because of these dissolved metals. Scientists discovered clues about this ancient chemistry hidden inside layered rock formations called banded iron formations. These rocks contain alternating layers rich in iron oxides, suggesting something dramatic eventually changed ocean chemistry. At some point, oxygen began reacting with the dissolved iron, causing it to precipitate and settle onto the seafloor as rust-like minerals. Those rocks became one of the most important records of Earth's atmospheric transformation. But during this chapter of the story, oxygen still remained extremely rare, and perhaps even more surprising, that may have helped protect the planet from freezing. The early sun was significantly weaker than it is now. Based on current astrophysical models, Earth should have received far less solar energy billions of years ago. By simple calculations, the oceans should have frozen solid. Yet, geological evidence indicates liquid water persisted across much of the planet. Scientists still wrestle with this contradiction, known as the faint young sun paradox. Methane and carbon dioxide remain two of the leading explanations. Both gases trap heat effectively, and methane may have been especially important under low oxygen conditions. In today's atmosphere, methane breaks down relatively quickly because oxygen and ultraviolet-driven chemistry destroy it. But in an oxygen-poor world, methane could accumulate much more easily, too. Some models suggest methane concentrations may have reached hundreds of times modern levels. Ironically, the absence of oxygen may have helped keep Earth warm enough for life to survive. This creates one of the great paradoxes in Earth's history. Oxygen feels essential now, yet early life may have depended on a world without it. In fact, oxygen is chemically aggressive. It reacts easily with other substances, which makes it useful for complex organisms needing large amounts of energy. But that same reactivity also makes oxygen dangerous. High concentrations can damage cells, proteins, and DNA. Modern organisms survive only because billions of years of evolution built protective systems capable of handling oxygen safely. Early life had no such protection. To many ancient microbes, oxygen would have functioned almost like a toxic environmental contaminant. And this raises a fascinating possibility. 2. When oxygen finally began spreading through the atmosphere later in Earth's history, some of the planet's earliest organisms may have experienced it not as progress, but as catastrophe. Entire ecosystems, adapted to oxygen-free environments, would have faced extinction as atmospheric chemistry changed. But before that transformation arrived, Earth remained trapped inside an uneasy balance. Volcanic activity continued feeding gases into the atmosphere. Oceans absorbed carbon dioxide. Primitive microbes slowly altered chemistry in localized environments. The surface remained hostile to modern life. Ultraviolet radiation from the sun bombarded the planet because no ozone layer existed yet. Land surfaces may have remained mostly barren rock exposed directly to harsh solar radiation. If life existed on land at all, evidence has not survived clearly. Most researchers suspect the oceans provided safer environments, where water offered some protection from ultraviolet exposure. Deep underwater, early microbial worlds may already have been astonishingly diverse despite their microscopic size. Different organisms evolved different survival strategies, feeding on sulfur compounds, dissolved iron, hydrogen gas, or organic molecules drifting through the oceans. Some may have clustered into layered microbial mats along shallow coastlines. Structures similar to stromatolites still found in rare environments today. These strange formations, built gradually by microbial communities trapping sediment and minerals, became some of the oldest widely accepted evidence of life on Earth. Looking at stromatolites now feels almost surreal because they appear so simple compared to modern forests or animals. Yet, organisms like these may represent the ancestors of every complex living thing that would eventually exist. The entire future biosphere of Earth may trace back to tiny microbial worlds hidden beneath oxygen-free seas. And somewhere within those microbial communities, evolutions stumbled upon a discovery that would permanently alter the atmosphere, the oceans, the climate, and the future of life itself. At first, the change may have seemed insignificant. Certain microorganisms began using sunlight in a new way. Instead of relying purely on chemical reactions from volcanic compounds or hydrothermal systems, They captured solar energy directly. A primitive photosynthesis had likely existed in some form before, but eventually a revolutionary version emerged, one capable of splitting water molecules apart and releasing oxygen as waste. The organisms responsible were ancestors of what scientists now call cyanobacteria. They were microscopic, fragile, invisible to the naked eye. Yet their arrival may have been one of the most important moments in the history of the universe. Because, from the perspective of the ancient oxygen-free Earth, these microbes were not simply adapting to the environment. They were preparing to remake the planet itself, too. For most of Earth's early history, the atmosphere belonged to organisms that never needed oxygen, and in many cases could not survive in its presence at all. The oceans were dark with dissolved iron. Methane drifted through the air in concentrations almost unimaginable today. And microbial life spread quietly beneath ancient seas without realizing the planet itself was approaching one of the most violent transformations in its history. What makes this moment so unsettling is that the disaster did not arrive from space. No asteroid struck the planet. No supervolcano destroyed the sky overnight. The catastrophe came from life itself. Tiny organisms floating through shallow oceans began releasing a gas that would eventually poison much of the world they lived in. Today, that gas keeps complex life alive. Back then, it may have triggered one of the first mass extinctions Earth ever experienced. The organisms responsible were cyanobacteria, often called blue-green algae, even though they are technically bacteria rather than true algae. They were microscopic, yet their influence would eventually become planetary. Unlike earlier life forms relying purely on chemical reactions involving sulfur or volcanic compounds, cyanobacteria evolved a powerful innovation. They use sunlight to split water molecules apart, extracting energy while releasing oxygen as waste. That single metabolic trick changed the future of Earth forever. At first, the oxygen they produced probably seemed insignificant. The ancient oceans contained enormous amounts of dissolved iron and other chemicals eager to react with oxygen immediately. Any oxygen entering seawater was quickly absorbed. Iron oxidized and settled onto the seafloor as rust-like minerals. Over immense spans of time, this process created the layered geological structures now known as banded iron formations. Some of the most important evidence scientists possess for reconstructing Earth's atmospheric history. Entire mountains of iron ore. Mine today may ultimately owe their existence to microscopic organisms living billions of years ago. It is strange to think that modern skyscrapers, bridges, ships, and cities are partially built from the chemical remains of one of Earth's earliest biological revolutions. Yet for a long time, oxygen still struggled to escape into the atmosphere itself. The oceans acted giant chemical sponges, consuming oxygen almost as fast as cyanobacteria produced it. But eventually something changed. Scientists still debate the exact timing and complexity of the transition. Yet around 2.4 billion years ago, oxygen began accumulating in the atmosphere in measurable amounts. Researchers call this event the Great Oxidation Event, though the name almost sounds too calm for what may actually have happened. From the perspective of ancient anaerobic organisms, this was not progress, it was environmental collapse. Oxygen is chemically aggressive, damages cells, proteins, and genetic material unless organisms evolve protective systems against it. And many early microbes had evolved in completely oxygen-free conditions and lacked any defense against oxidative damage. As oxygen concentrations increased, entire ecosystems may have faced extinction. Some researchers believe vast populations of anaerobic organisms retreated into isolated environments where oxygen remained scarce, such as deep sediments, hydrothermal systems, or oxygen-poor waters. Even today, descendants of ancient anaerobic life still survive in places where oxygen remains limited. In a sense, parts of the ancient Earth never fully disappeared. They simply retreated underground and underwater. The atmosphere itself also began changing in dramatic ways. Methane, once one of the dominant greenhouse gases helping warm the planet beneath the faint young sun, reacted with increasing oxygen levels and began breaking down. This may have triggered one of the greatest climate shifts in Earth's history. Some scientists suspect the collapse of atmospheric methane caused temperatures to plummet globally, possibly contributing to enormous glaciations. Evidence suggests parts of Earth may have entered episodes of extreme freezing, sometimes referred to as Snowball Earth conditions, where ice expanded across much of the planet. The exact severity of these events remains debated, but the possibility is astonishing. Oxygen may not only have poisoned ancient life, it may also have nearly frozen the world. Imagine the irony. The same gas that would eventually allow animals, forests, and humans to exist may first have plunged Earth into environmental catastrophe. This dual nature of oxygen sits at the center of one of the deepest themes in Earth's history. What saves one form of life may destroy another. Evolution does not move toward comfort. It moves through instability, adaptation, collapse, and survival. The rise of oxygen transformed not only biology, but also the chemistry of the oceans, atmosphere, and rocks themselves. Before oxygen accumulated, large amounts of iron remained dissolved in seawater. After oxygen spread, iron oxidized more rapidly and precipitated out of the oceans. Chemistry of the seas shifted permanently. Minerals formed differently. Weathering processes changed. The atmosphere for itself became increasingly unlike anything that had existed before. Yet, oxygen levels during the Great Oxidation Event were still probably far lower than modern levels. The transformation unfolded over immense periods of time, perhaps with fluctuations, reversals, and unstable phases. Researchers are still trying to understand. Some geological evidence hints that oxygen may have risen temporarily before falling again multiple times. The ancient atmosphere may have remained chemically unstable for hundreds of millions of years. Scientists continue debating how rapidly oxygen accumulated and how directly cyanobacteria alone drove the transition. Volcanic activity, tectonic shifts, ocean chemistry, and burial of organic carbon may all have played important roles. The deeper researchers investigate the event, the more complicated it becomes. But one reality remains difficult to escape. Life was no longer merely adapting to Earth. Life had begun reshaping the planet on a global scale. This realization completely changes the way scientists think about atmospheres on other worlds. A planet's atmosphere may not simply reflect geology or climate. It may also reflect biology. Oxygen itself became one of the strongest potential biosignatures astronomers search for when studying distant exoplanets, because on Earth, abundant oxygen is deeply tied to life. Yet Earth's own history also warns that oxygen is not guaranteed to appear quickly or remain stable once it does. For billions of years, life existed without large amounts of atmospheric oxygen. And even after oxygen-producing organisms evolved, the atmosphere resisted change for immense stretches of time. This creates a fascinating possibility. Alien worlds may already contain life while still appearing chemically lifeless from a distance. During this transition, the appearance of Earth itself may have changed dramatically. Methane haze could have thinned as oxygen increased. The sky may gradually have become clearer and bluer, though the exact timing remains uncertain. Sunlight penetrating the atmosphere would have behaved differently as atmospheric chemistry evolved. The oceans changed color too. Iron-rich green waters slowly became chemically transformed. Ancient coastlines, populated by microbial mats, may have expanded and collapsed repeatedly, depending on changing environmental conditions. Yet, despite all the destruction oxygen caused, it also unlocked extraordinary new possibilities. Oxygen allows organisms to generate energy far more efficiently than many anaerobic chemical pathways. Complex, multicellular life demands enormous amounts of energy, and oxygen eventually made that possible. In a sense, the rise of oxygen expanded the energetic limits of biology itself. Without it, large animals, advanced nervous systems, active movement, and eventually humans may never have evolved. But during the Great Oxidation Event, none of that future existed yet. The atmosphere was still becoming something new. Earth was caught between two worlds, the ancient methane-rich planet of anaerobic microbes and the future oxygen-rich world of complex life, and the transition may have been brutal. Some researchers even describe oxygen as Earth's first major pollution crisis. Cyanobacteria filled the environment with a reactive waste product that countless existing organisms could not tolerate. The comparison feels strangely modern, a living system altering the atmosphere globally, triggering climate shifts and mass ecological consequences. Except this happened billions of years before animals even existed. There is another haunting possibility hidden inside this story. Oxygen may not have risen purely because cyanobacteria suddenly evolved. Some scientists suspect oxygen production may have existed earlier, but geological systems initially absorbed it completely. Only after volcanic gases changed, continental growth increased, or organic carbon burial intensified, did oxygen begin escaping into the atmosphere permanently. If true, then Earth may have spent enormous stretches of time balancing right on the edge of atmospheric transformation without crossing it. That possibility makes the Great Oxidation Event feel less like a single moment and more like a planetary tipping point, reached after countless interacting processes aligned together. And once oxygen finally began accumulating, Earth could never fully return to what it had been before. The atmosphere had crossed into a new state. The chemistry of the oceans changed. Climate systems shifted. Entire branches of life disappeared while others adapted and diversified. The ancient world without oxygen was fading away, but another transformation was still waiting above the planet, because oxygen alone was not enough to protect life on land. High in the atmosphere, sunlight would soon begin reshaping oxygen into something equally important, a fragile, invisible shield that would change the future of Earth once again. For billions of years, life on Earth remained trapped beneath water, as if the planet itself were warning organisms not to climb any higher. Oceans protected early life from dangers that existed far above the surface, dangers invisible to human eyes, yet powerful enough to damage cells, destroy genetic material, and sterilize exposed land. the sky may have looked calmer after oxygen began spreading through the atmosphere. But sunlight carried a hidden threat that the ancient Earth still had no defense against. Ultraviolet radiation from the sun poured through the atmosphere almost unchecked, bombarding coastlines, shallow pools, and barren rock with energy capable of tearing apart delicate biological structures. In a world without protection from ultraviolet light, land remained hostile even after oceans stabilized and oxygen levels slowly rose. Yet somewhere high above the planet, oxygen itself was beginning to change into something new. And that transformation would eventually allow forests, animals, insects, dinosaurs, and humans to step onto dry land. The strange thing about ozone is that it is made from the same oxygen modern life depends on, but arranged differently. Ordinary oxygen contains 2 oxygen atoms bonded together. Ozone contains 3. That extra atom makes ozone unstable and reactive, but also extraordinarily important. High in the atmosphere, ultraviolet radiation from the sun splits oxygen molecules apart. Some of those free oxygen atoms then collide with other oxygen molecules, forming ozone. Over immense stretches of time, enough ozone accumulated in the upper atmosphere to create a thin protective layer surrounding the planet. And despite being incredibly fragile and relatively small in total volume, that layer changed Earth forever. Without it, complex life on land may never have evolved. It is difficult to overstate how dangerous ultraviolet radiation can be for living organisms. Certain wavelengths damage DNA directly, interfering with reproduction and cellular repair. In modern humans, overexposure contributes to skin cancer and other forms of tissue damage. But for early life forms without advanced protective adaptations, the danger would have been even greater. Before ozone accumulated, shallow land surfaces may effectively have been sterilized repeatedly by solar radiation. Water acted like a shield, absorbing and scattering much of that ultraviolet energy. Even a few feet beneath the ocean surface offered significantly more protection than exposed rock under open sky. This may explain why life remained marine for such an immense portion of Earth's history. The oceans were not simply where life began, they were where life hid. As ozone levels gradually increased, conditions near the surface slowly became less hostile. Ultraviolet radiation reaching the ground decreased enough for organisms to survive longer outside water. The transition probably unfolded gradually, rather than as a sudden planetary switch. Different regions of Earth may have become more or less habitable depending on atmospheric conditions, altitude, cloud cover, and oxygen concentrations. But eventually, the balance shifted enough that life began experimenting with the land itself. And once it did, Earth started transforming again. At first, the earliest life on land was likely simple. Microbial films, primitive fungi, and early photosynthetic organisms may have spread across damp surfaces long before forests or animals appeared. Some researchers believe microbial communities may already have colonized parts of the land surprisingly early, perhaps living inside rocks or sheltered environments where radiation exposure was reduced. But truly complex terrestrial ecosystems required more stable atmospheric protection. Once that protection improved, evolution accelerated into entirely new directions. Plants became especially important. Early land plants faced enormous challenges. Water had supported their ancestors physically inside oceans, but on land gravity became a constant force. Dry air increased the risk of dehydration. Reproduction became more complicated without surrounding water. Yet plants gradually evolved structures capable of surviving these conditions: waxy coatings to reduce water loss, vascular systems to transport fluids internally, roots to anchor into soil, and eventually seeds capable of surviving harsher environments. As plants spread across continents, they altered the atmosphere and climate in profound ways. Through photosynthesis, plants absorbed carbon dioxide and released oxygen continuously. Vast forests eventually covered large portions of Earth, drawing huge amounts of carbon from the atmosphere and locking it into wood, soils, and sediments. Some scientists suspect the expansion of land plants contributed to major climate shifts by reducing greenhouse gases. Weathering processes also intensified because plant roots broke apart rock and increased chemical interactions between the atmosphere and surface minerals. Earth was no longer shaped solely by volcanoes, oceans, and tectonics. Biology itself had become a geological force. During certain ancient periods, oxygen levels may have climbed far higher than modern concentrations. 2. One of the most fascinating examples occurred during the Carboniferous period around 300 million years ago. Enormous swamp forests spread across warm, wet landscapes, burying vast amounts of organic carbon that later became coal deposits. Because so much carbon was trapped underground, instead of returning quickly to the atmosphere as carbon dioxide, oxygen levels may have risen dramatically. Some estimates suggest atmospheric oxygen reached around 30 to 35%, compared to about 21% today. That difference may help explain one of the strangest chapters in Earth's biological history. Giant insects. Dragonfly-like creatures with wingspans over 2 feet wide. Massive millipedes stretching several feet long. Enormous arthropods crawling through ancient forests unlike anything alive today. Scientists still debate exactly how much elevated oxygen contributed to these gigantic sizes, but oxygen likely played a major role. Insects breathe differently than mammals, relying partly on passive diffusion through tiny openings in their bodies. Higher oxygen concentrations may have allowed oxygen to move more efficiently through larger bodies, supporting sizes impossible under modern atmospheric conditions. Earth's atmosphere was not just supporting life anymore. It was influencing the physical scale and evolutionary possibilities of entire ecosystems. And yet, despite the stabilizing influence of ozone, the atmosphere remained delicate and dynamic. Ozone itself forms and breaks apart constantly. 2. It exists in a balance driven by sunlight, atmospheric chemistry, and circulation patterns. Even relatively small disruptions can affect it. Modern humanity learned this painfully during the 20th century, when scientists discovered that industrial chemicals called chlorofluorocarbons, or CFCs, were damaging the ozone layer. In Antarctica, ozone thinning became severe enough to create what became known as the ozone hole. The discovery deeply unsettled scientists because it revealed how dependent complex life remains on a protective atmospheric layer most people never think about. Without ozone, ultraviolet exposure would increase significantly, damaging ecosystems and human health alike. The atmosphere that allowed life onto land remains vulnerable even now. Looking back across deep time, the ozone layer almost feels like an invisible border separating two different Earths. Before ozone, life belonged mostly to the oceans. After ozone, continents transformed into biological worlds filled with forests, rivers, insects, reptiles, mammals, and eventually civilizations. Yet, that transformation may also have reshaped the planet's climate in unexpected ways. Plants pulled carbon dioxide from the atmosphere while increasing oxygen. Forests influenced rainfall patterns and temperatures. Soil formation accelerated. Organic matter accumulated in vast quantities. Earth became greener, wetter, and biologically more complex. Some scientists even argue that life itself helped stabilize climate through feedback systems involving carbon cycling, vegetation, and atmospheric chemistry. This idea remains debated in detail, but the broader pattern is difficult to ignore. Life did not simply adapt to Earth. Life increasingly altered Earth. There is also a deeper cosmic question hidden inside this chapter of the story. Is ozone inevitable on worlds with oxygen-rich atmospheres? Or was Earth unusually fortunate? Astronomers searching for habitable exoplanets often consider ozone an important atmospheric clue because it may indicate both oxygen and protection from ultraviolet radiation. Some telescopes attempt to detect ozone signatures in distant planetary atmospheres for exactly this reason. But Earth's history suggests habitability is not binary, it evolves. A planet may possess water, yet remain hostile to land life for billions of years. It may contain microbial ecosystems long before forests or animals become possible. Path from simple life to complex surface ecosystems may depend on countless interacting variables. Volcanic activity, oxygen production, atmospheric chemistry, magnetic protection, solar behavior, tectonic cycles, and perhaps pure chance. And Earth itself almost certainly experienced setbacks along the way. Oxygen levels fluctuated dramatically across geological history. Climate shifts triggered extinctions repeatedly. Volcanic eruptions and asteroid impacts periodically destabilized ecosystems. The atmosphere was never permanently solved. It remained an active system, constantly changing alongside life itself. Yet despite all those instabilities, one reality became increasingly clear after ozone spread through the upper atmosphere. The surface of Earth was no longer biologically empty. Life had escaped the oceans. Forests rose across continents. Rivers carried nutrients through growing ecosystems. Creatures crawled, flew, hunted, and evolved beneath a protected sky. The atmosphere that once could not support breathing had become a shield, powerful enough to help complex life dominate the land. But hidden beneath that success was another unsettling truth. Earth's atmosphere had already changed catastrophically before, and it would do so again. Because the same atmosphere that protects life can also threaten it when the balance shifts too far. From the perspective of human history, Earth's atmosphere feels stable, almost permanent. The sky appears every morning with the same familiar blue. Oxygen levels remain nearly unchanged across generations. Seasons come and go inside predictable patterns. But when scientists look deeper into geological time, the atmosphere tells a far more unsettling story. Again and again, the air surrounding Earth has shifted dramatically enough to nearly destroy the living world beneath it. Entire climates have collapsed. Oceans have lost oxygen. Temperatures have swung toward extremes almost beyond imagination. Ice advanced across continents that once held forests, while greenhouse conditions later transformed frozen regions into swamps and shallow seas. The atmosphere that protects life has repeatedly come dangerously close to becoming its executioner. One of the strangest examples may have occurred during the Snowball Earth episodes, periods when large portions of the planet may have frozen over almost completely. The exact severity of these events remains debated, but geological evidence suggests Earth experienced extraordinary glaciations hundreds of millions of years ago. Ice may have extended from the poles toward the equator. Tropical oceans could have frozen beneath dim sunlight, reflecting off enormous sheets of white ice. Imagine standing on Earth during such a time. The planet would no longer resemble the green world familiar today. Winds would move across frozen plains stretching for thousands of miles. The oceans, where life first emerged, would become sealed beneath expanding ice. Sunlight, reflecting from the frozen surface, would cool the planet even further, reinforcing the freeze in a terrifying feedback loop. And all of this may have been connected to changes in atmospheric chemistry. Carbon dioxide and methane play enormous roles in trapping heat inside Earth's atmosphere. When their concentrations drop significantly, global temperatures can fall rapidly. Some scientists believe the rise of oxygen earlier in Earth's history reduced atmospheric methane enough to weaken greenhouse warming dramatically, contributing to ancient glaciations. Other factors may also have been involved. Continents drifting toward tropical regions could have increased weathering, pulling carbon dioxide from the atmosphere faster. Volcanic activity may have shifted. Ocean circulation may have changed. The deeper researchers investigate these frozen worlds, the more they realize Earth's climate depends on interconnected systems balancing against each other constantly. 2. What makes Snowball Earth especially fascinating is that life appears to have survived despite the severity of the conditions. Scientists still debate exactly how complete the freezing became. Some models suggest thin bands of open water may have persisted near the equator. Others propose hydrothermal vents beneath the oceans provided refuges for microbial ecosystems. Certain researchers argue the ice never fully sealed every ocean surface, while others believe Earth may genuinely have resembled a frozen white sphere drifting through space. Regardless of the details, survival itself seems remarkable. It suggests life on Earth can endure environmental disasters far beyond what humans normally imagine possible. Yet survival often came at enormous cost. Atmospheric changes repeatedly reshaped ecosystems across geological history, sometimes triggering extinctions so severe they nearly reset the trajectory of evolution itself. Among the most catastrophic events was the Permian mass extinction around 252 million years ago, often called the Great Dying. Unlike the asteroid impact that later killed the dinosaurs, the Permian extinction may have unfolded primarily through atmospheric and climate collapse driven by volcanic activity on an almost incomprehensible scale. In what is now Siberia, enormous volcanic eruptions known collectively as the Siberian Traps released staggering quantities of carbon dioxide, methane, sulfur compounds, and other gases into the atmosphere over extended periods. Lava covered immense regions of land. Ash and toxic gases spread globally. Climate systems destabilized rapidly. Temperatures climbed. Oceans warmed and lost oxygen. Entire marine ecosystems suffocated. Some estimates suggest more than 90% of marine species disappeared. Forests collapsed. Food chains shattered. Certain regions of Earth may have become nearly uninhabitable for complex life. The atmosphere itself became part of the extinction mechanism. As temperatures rose, oceans absorbed less oxygen. Warm, stagnant waters expanded. In some theories, deep ocean environments rich in hydrogen sulfide began releasing toxic gas into the atmosphere. Hydrogen sulfide is lethal even in relatively small concentrations. 2. Certain researchers have proposed that under extreme conditions, poisonous gases from oxygen-starved oceans may have spread into coastal environments, further worsening the catastrophe. The exact sequence of events remains debated, but the broader picture is deeply unsettling. Earth's atmosphere and oceans can amplify crises once climate systems cross dangerous thresholds. The planet does not always change gradually. Sometimes it shifts violently, and perhaps the most haunting part is that many of these changes emerged from processes already built into Earth itself. Volcanoes, carbon cycles, atmospheric feedbacks, ocean chemistry. Nothing alien needed to arrive from space. The atmosphere already contained the power to destabilize the world on its own. Even smaller atmospheric shifts have reshaped evolution repeatedly. During certain periods, oxygen levels rose high enough to fuel giant insects and massive wildfire activity. At other times, oxygen declined significantly, possibly placing stress on large animals dependent on high metabolic demands. Carbon dioxide levels fluctuated enormously over geological time, influencing temperature, sea level, rainfall patterns, and biodiversity. Continents drifting across the globe altered atmospheric circulation and ocean currents. Mountain building changed rainfall and weathering patterns. The atmosphere was never static. It evolved alongside geology and life in an endless exchange of influence. One of the most fascinating aspects of this story is how sensitive the climate system appears to be. Tiny percentages of atmospheric gases can determine whether Earth becomes warmer, colder, wetter, drier, or chemically unstable. Carbon dioxide today makes up only a small fraction of the atmosphere by volume, yet its influence on heat retention is enormous. Methane exists in even smaller concentrations, but traps heat extremely efficiently. Ozone, though incredibly thin, protects life from ultraviolet radiation. The atmosphere functions less like a simple blanket and more like a complex chemical machine balanced across interacting feedback loops. Sometimes those loops stabilize the planet. Sometimes they push it toward disaster. Venus offers perhaps the clearest warning of what runaway atmospheric change can become. Many planetary scientists believe Venus may once have possessed liquid water and more moderate conditions billions of years ago. But over time, greenhouse warming intensified until oceans evaporated. Water vapor itself amplified heating further because it is a powerful greenhouse gas. Eventually, the planet entered a runaway greenhouse state. Today, Venus possesses surface temperatures hot enough to melt lead beneath an atmosphere, crushing enough to destroy spacecraft within hours. Earth avoided that fate, but scientists continue debating how close the planet may have come at different points in its history. Mars reveals the opposite danger. Evidence strongly suggests ancient Mars once possessed rivers, lakes, and a thicker atmosphere. But because Mars is smaller, its internal heat faded faster. Its magnetic field weakened. Solar wind gradually stripped much of the atmosphere away. Without enough atmospheric pressure and greenhouse warming, surface water became unstable. The planet slowly transformed into the cold, dry world seen today. Earth exists between these extremes, yet not because stability was guaranteed. The atmosphere has remained habitable, partly because geological and biological systems continuously reshaped it together. Volcanoes recycle carbon into the atmosphere. Oceans absorb it. Plants remove carbon dioxide through photosynthesis. Tectonic activity buries and releases materials over millions of years. Weathering of rocks regulates greenhouse gases gradually. It is a dynamic equilibrium, not a permanent condition. And through deep time, that equilibrium has repeatedly drifted toward catastrophe before recovering again. Scientists argue Earth's climate system contains natural stabilizing feedbacks preventing permanent collapse under most conditions. Others caution that certain thresholds, once crossed, can trigger dramatic, irreversible changes. The debate continues because Earth's history contains evidence for both resilience and vulnerability. Life survived Snowball Earth conditions. Life survived mass extinctions. Yet countless species still vanished permanently during those crises. Recovery often required millions of years. Looking across this immense timeline changes the way the atmosphere feels. It is no longer merely air. It becomes an active force shaping evolution, extinction, climate, and survival. Every forest, ocean, desert, and ecosystem exists inside boundaries the atmosphere allows. Shift those boundaries far enough, and entire worlds disappear. Yet, despite all the disasters Earth endured, the atmosphere never fully collapsed into the extremes seen on Venus or Mars. Somehow, the planet maintained enough balance for life to persist through catastrophe after catastrophe. And hidden behind that stability may be another set of invisible protectors most people rarely think about. Forces extending far beyond the atmosphere itself, reaching deep into Earth's molten core and outward into space around the planet. When people imagine what keeps Earth alive, they usually think about air, water, sunlight, maybe forests or oceans. But some of the most important systems protecting life are almost completely invisible. They stretch far above the atmosphere, deep beneath the crust, and even outward into space itself. Without them, Earth's atmosphere may never have survived long enough for complex life to evolve at all. In many ways, the story of Earth is not simply the story of a planet that formed in the right place. It is the story of a planet that somehow kept avoiding destruction through a series of protections most worlds may never receive. And some of those protections began with catastrophe. Long before forests, oceans, or even stable continents existed, something enormous slammed into the young Earth. Scientists believe a protoplanet roughly the size of Mars collided with Earth during the solar system's violent early formation period. The impact was so powerful that entire portions of both worlds were vaporized instantly. Rock blasted into orbit around the planet in glowing streams of debris. For a time, Earth itself may have resembled a partially molten sphere wrapped in expanding clouds of superheated material. Out of that destruction, the moon formed. At first glance, the moon seems almost passive in Earth's story. It hangs silently in the sky, controlling tides and lighting the night. But many scientists suspect the moon may be one of the hidden reasons Earth remained stable enough for life to survive. Without it, the planet itself might behave very differently. Earth rotates on a tilted axis. That tilt creates seasons as different hemispheres receive varying amounts of sunlight throughout the year. But axial tilt is not always stable on every planet. Mars, for example, experiences dramatic variations in tilt over long periods because it lacks a large stabilizing moon. Some models suggest Mars's axis may swing chaotically across geological timescales, producing severe climate shifts. Earth's moon, however, acts almost like a gravitational anchor, helping stabilize the planet's tilt. This stability may have prevented climate extremes that could otherwise destabilize ecosystems repeatedly. Without the moon, Earth's axial tilt might wander far more dramatically. Imagine a world where the poles sometimes point much more directly toward the sun before shifting again over millions of years. Entire climate systems could reorganize. Ice sheets might expand and collapse unpredictably. Tropical regions could drift into colder conditions, while frozen areas warmed. Some scientists believe complex life would struggle to evolve under highly unstable long-term climates. The moon may have quietly reduced that chaos for billions of years, and that is only one possibility. The moon also drives Earth's tides through gravity. Today, tides feel ordinary, but on the ancient Earth, they may have been far more dramatic because the moon orbited closer to the planet. Vast tidal movements could have shaped shallow coastal environments where early chemistry and biological evolution unfolded. Some researchers speculate that tidal cycles may have helped concentrate organic molecules repeatedly in coastal pools, potentially assisting prebiotic chemistry long before complex life existed. Others argue tidal mixing influenced ocean circulation and nutrient distribution across ancient seas. These ideas remain debated. But the deeper scientists investigate Earth's history, the harder it becomes to separate biology from planetary mechanics. The atmosphere itself may partially owe its survival to forces extending far beyond the air. One of the most important invisible systems protecting Earth is the magnetic field. Most people notice it directly, yet without it, the atmosphere could face constant assault from space. Deep inside Earth's core, molten iron moves through complex convection currents driven by heat escaping from the planet's interior. That movement generates electric currents, which in turn create Earth's magnetic field through a process known as the geodynamo. The field extends outward into space, surrounding the planet in an invisible protective bubble called the magnetosphere, and it is constantly under attack. The sun does not simply emit light and heat. It also releases streams of charged particles known as the solar wind. During solar storms, enormous bursts of energetic particles erupt outward across the solar system. Without magnetic protection, those particles can gradually erode atmospheres over immense periods of time. Mars provides one of the clearest examples of what happens when that protection weakens. Billions of years ago, Mars likely possessed a thicker atmosphere, flowing water, lakes, and perhaps even shallow seas. But the planet is smaller than Earth, meaning its interior cooled faster. As its core cooled, Mars lost much of its global magnetic field. Without strong magnetic protection, solar wind gradually stripped away large portions of the atmosphere. Over time, surface pressure dropped. Liquid water became unstable. The world dried and froze. Today, Mars remains cold, thin-aired, and exposed beneath harsh radiation. Looking at Mars feels unsettling, because it may represent a version of planetary history Earth narrowly avoided. Earth's magnetic field acts like a shield, deflecting many charged particles before they reach the atmosphere directly. Some particles still slip through near the poles, creating auroras as they collide with atmospheric gases high above the planet. Those shimmering lights are beautiful reminders that space around Earth is not calm. It is active, violent, and filled with radiation. The magnetosphere absorbs impacts from that environment constantly. Without it, the atmosphere could gradually weaken over geological timescales. Some researchers even suspect the magnetic field helped preserve Earth's oceans by reducing atmospheric loss early in the planet's history, when solar activity was likely more intense. Yet even this protection is not perfectly stable. Earth's magnetic field changes continuously. Magnetic poles wander over time and occasionally reverse completely. Geological records reveal many magnetic reversals throughout Earth's history, where north and south poles swapped positions. Scientists still debate how much atmospheric or biological impact these reversals produce, but they demonstrate that the protective systems surrounding Earth are dynamic rather than fixed. The planet survives through constant motion and adjustment, not permanent equilibrium. There is another layer of protection humans rarely think about: Jupiter. The solar system's largest planet may also influence Earth's long-term stability in complicated ways. Because of its immense gravity, Jupiter affects the movement of asteroids and comets throughout the solar system. Some scientists describe Jupiter as a kind of cosmic shield because it can deflect or absorb certain incoming objects that might otherwise threaten the inner planets. Yet the story is not entirely simple. In some orbital configurations, Jupiter's gravity may also redirect dangerous objects inward toward Earth-crossing paths. The giant planet acts less like a perfect guardian and more like a massive gravitational architect, shaping the traffic patterns of the solar system itself. Even so, the arrangement of planets likely influenced Earth's bombardment history, climate cycles, and long-term orbital stability. Once again, Earth's survival appears tied to interacting systems extending far beyond the atmosphere alone. The more scientists study planetary habitability, the stranger the picture becomes. Life does not depend only on having liquid water or the right distance from a star. Habitability may also require long-term climate stability, geological activity, atmospheric retention, magnetic shielding, chemical cycling, and perhaps even the presence of a large moon. Some researchers refer to this as the rare Earth hypothesis, the idea that complex life may require an unusually specific combination of conditions that few planets achieve simultaneously. Not all scientists agree with this conclusion. Some argue life may adapt to far wider conditions than currently understood. Others point out that humanity possesses data from only one living planet, making it dangerous to draw strong conclusions about rarity. Still, Earth's history increasingly appears less straightforward than once imagined. The atmosphere did not survive automatically. It survived through interacting layers of protection and feedback extending from the planet's core to the outer solar system. And even with all those protections, Earth still experienced repeated climate catastrophes, mass extinctions, and atmospheric instability. The atmosphere remained habitable, not because danger disappeared, but because the planet repeatedly recovered. Sometimes recovery itself depended on geological systems hidden deep underground, plate tectonics, recycled carbon between Earth's interior, oceans, and atmosphere over immense timescales. Volcanic activity replenished gases. Weathering removed carbon dioxide gradually. Oceans stored heat and chemicals. Life altered atmospheric composition continuously. Earth functioned almost like a giant interconnected machine, balancing destructive and stabilizing forces together. Remove enough pieces from that machine, and the story may end very differently. One of the most haunting realizations in planetary science is that habitability may be temporary. A planet can possess oceans, atmosphere, and stable climates for billions of years before conditions change irreversibly. Stars evolve, magnetic fields weaken, atmospheres escape, geological activity fades. Earth itself will not remain habitable forever. The sun grows slightly brighter over time. Billions of years from now, increasing solar energy may trigger stronger evaporation and greenhouse warming. Oceans could gradually disappear. Atmospheric chemistry will change again. In the deepest future, Earth may resemble a hotter, drier world long before the sun finally dies. The atmosphere protecting life today is part of a temporary chapter in planetary history, not a permanent condition. Yet right now, in this narrow moment between ancient catastrophe and distant collapse, Earth remains astonishingly balanced. A magnetic shield still deflects solar storms. The moon still stabilizes the planet's tilt. Oceans still cycle heat around the globe. The atmosphere still holds enough oxygen for forests, animals, and civilizations to breathe beneath a protected sky. And perhaps the strangest part is that all of this emerged from a universe where lifeless planets appear far more common than living ones. Which raises a question scientists are still struggling to answer. If Earth required so many invisible protections to remain habitable, how many other worlds out there ever truly get the chance to breathe? For most of human history, people looked at the night sky and imagined the stars as unreachable lights scattered across an endless darkness. But now, for the first time, humanity has begun discovering that many of those stars are surrounded by worlds of their own. Some are giant planets wrapped in storms larger than Earth itself. Others are frozen wastelands drifting through eternal darkness. Some orbit two suns. Some may have oceans beneath thick atmospheres. And somewhere among them could exist planets with skies, weather, clouds, and perhaps even forms of life, breathing beneath alien atmospheres no human has ever seen. The deeper scientists search, the stranger the universe becomes. What surprises researchers most is not that planets exist, but how many there appear to be. Before the 1990s, humanity had never confirmed a single planet orbiting another sun-like star. Today, thousands of exoplanets have been identified, and astronomers suspect there may be billions more in the Milky Way alone. Some systems contain planets orbiting so close to their stars that entire years last only days. Others contain massive worlds drifting farther from their stars than Neptune does from the Sun, and hidden among those discoveries are planets that seem strangely familiar. Rocky worlds roughly similar in size to Earth, orbiting within regions where temperatures might allow liquid water to exist. Scientists often call this the habitable zone, though the phrase can be misleading because habitability depends on far more than distance alone. Earth's own history already proved that. A planet can sit in the right region around a star and still lose its atmosphere, freeze solid, overheat catastrophically, or remain biologically sterile for billions of years. Yet despite those uncertainties, atmospheres remain one of the first things astronomers search for when studying distant worlds, because in many ways, a planet's atmosphere tells the story of the planet itself. Atmospheres reveal temperature, chemistry, weather, pressure, and possibly even biology. The challenge is that these planets are unimaginably far away. Most cannot be photographed directly with current technology because their stars outshine them completely. Instead, astronomers often detect exoplanets indirectly. One common method involves watching stars carefully for tiny dips in brightness. 2. If a planet passes in front of its star from Earth's perspective, it blocks a small amount of light. From those dimming patterns, scientists can estimate the planet's size, orbit, and sometimes even clues about its atmosphere. And this is where the story becomes almost unbelievable. When starlight passes through a planet's atmosphere during one of these transits, certain wavelengths are absorbed by atmospheric gases. By studying the missing patterns in the light, astronomers can identify chemical signatures from atmospheres hundreds or even thousands of light years away. In other words, humanity has learned how to read the chemistry of alien skies using starlight itself. Through these techniques, scientists have already detected atmospheres containing hydrogen, helium, sodium, water vapor, methane, and carbon dioxide on distant worlds. Some planets appear wrapped in thick clouds of vaporized metals. Others may experience rains of molten glass driven sideways by violent winds. There are worlds so hot that entire atmospheres glow beneath constant stellar radiation. Some gas giants orbit so close to their stars that their outer atmospheres are literally evaporating into space. The universe keeps producing environments stranger than science fiction imagined. Yet, among all these discoveries, one question dominates the search. Could any of these planets actually support life? Oxygen attracts enormous attention because on Earth, large amounts of atmospheric oxygen are strongly connected to biology. Plants, algae, and cyanobacteria transformed Earth's atmosphere over billions of years. So when astronomers search for life elsewhere, oxygen often becomes one of the primary targets. Ozone matters too, because it may indicate oxygen-rich atmospheres protected from intense ultraviolet radiation. Methane is another intriguing gas because biological processes produce significant amounts of it on Earth. Some scientists focus on combinations of gases that should not coexist naturally for long without constant replenishment. Oxygen and methane together, for example, can signal chemical disequilibrium, potentially maintained by living systems. But Earth's own history warns scientists to be cautious. Oxygen is not a perfect biosignature. For billions of years, life existed on Earth without abundant atmospheric oxygen. Alien planets could host oceans full of microbial ecosystems while still appearing lifeless to distant telescopes. On the other hand, oxygen can also accumulate through non-biological processes under certain conditions. A planet losing water to space, for example, might leave behind oxygen-rich atmospheres without any life involved at all. The same atmosphere that seems promising from afar could turn out to be sterile. This uncertainty forces scientists to think beyond Earth-like assumptions. What if alien life does not rely on oxygen at all? On early Earth, anaerobic organisms thrived long before oxygen-rich ecosystems evolved. Some researchers speculate that methane-rich atmospheres could support entirely different biological systems under the right conditions. Others study the possibility of life in subsurface, oceans hidden beneath ice-covered moons like Europa or Enceladus within our own solar system. These environments may never possess breathable atmospheres on the surface, yet liquid water and chemical energy still exist beneath the ice. The deeper scientists explore extremophiles on Earth, organisms surviving in acid, radiation, freezing cold, crushing pressure, or toxic chemistry. The harder it becomes to define where life truly cannot exist. Some microbes on Earth survive inside rocks miles beneath the surface. Others live near hydrothermal vents hotter than boiling water. Certain bacteria endure radiation levels that would kill humans instantly. Life repeatedly demonstrates a terrifying flexibility. This possibility changes the search for habitable worlds completely. Perhaps the universe does not require Earth-like conditions as often as once believed. Or perhaps complex, intelligent life remains extraordinarily rare, even if microbial life is common. Scientists still argue intensely over this question because the evidence remains frustratingly incomplete. And then there is the Fermi paradox, one of the most unsettling ideas in modern science. If planets are so common and the universe is so vast, where is everybody? The Milky Way alone contains hundreds of billions of stars. Many likely possess planets. Statistically, some should resemble Earth at least loosely. Given enough time, intelligent civilizations might emerge repeatedly. Yet humanity sees no clear evidence of advanced extraterrestrial life. No signals, no visible engineering, no confirmed contact. Some scientists argue intelligent life may simply be extremely rare. Others suggest civilizations tend to destroy themselves before spreading far into space. 2. Certain researchers think the distances between stars make communication and travel vastly harder than popular imagination assumes. There are even darker possibilities. Maybe habitable worlds frequently lose atmospheric stability before complex life has enough time to develop. Earth's own history shows how fragile planetary balance can be. A slightly weaker magnetic field, different volcanic cycles, altered greenhouse chemistry, or unstable orbital dynamics might have changed everything. Some planets may begin habitable and later die. Others may remain biologically stagnant for billions of years. And perhaps some worlds breathe in ways humans would barely recognize. Scientists have already discovered planets unlike anything in the solar system. Super-Earths several times more massive than our planet. Ocean worlds potentially covered entirely by global seas hundreds of miles deep. Mini Neptunes wrapped in thick hydrogen atmospheres. 2 worlds tidally locked to red dwarf stars, where one side faces permanent daylight while the other remains trapped in eternal night. On some of these planets, atmospheric circulation could create bizarre climates with violent winds, transporting heat between hemispheres continuously. Certain models suggest habitable regions might exist only within narrow twilight zones between scorching and frozen sides. Even clouds could behave differently under alien gravity and chemistry. Some atmospheres may contain photochemical hazes, turning skies orange, purple, or black. Others might never produce blue skies at all. The more astronomers learn, the more Earth stops looking typical. Yet Earth also reveals something hopeful. Atmospheres can evolve dramatically over time. The young Earth once lacked oxygen. Oceans formed gradually. Ozone accumulated later. Complex life emerged only after billions of years of atmospheric transformation. A distant exoplanet appearing hostile today might simply be younger in its evolutionary journey. 2. Somewhere out there, another planet could currently be passing through its own version of Earth's ancient methane-rich world, or its oxygen revolution, or its first stable oceans. We may be observing worlds at completely different chapters of planetary history without realizing it, and perhaps the strangest realization of all is this: every breath taken by every animal, every forest releasing oxygen, every cloud drifting through Earth's atmosphere is part of a planetary story shaped across billions of years by geology, chemistry, sunlight, catastrophe, and life itself. The atmosphere surrounding Earth is not ordinary. It is the product of an almost incomprehensibly long chain of events, which raises a haunting possibility. If another world out there truly breathes beneath alien skies tonight, its atmosphere may carry a history just as violent, fragile, and improbable as our own. If you could leave Earth and drift far enough into space to see the entire planet at once, one detail would stand out almost immediately: the atmosphere protecting every ocean, forest, city, and living creature on Earth is unbelievably thin. From orbit, it appears less like a vast sky and more like a fragile, glowing membrane wrapped around a dark sphere. Compared to the size of the planet itself, the layer containing nearly all breathable air is thinner than the skin on an apple. Everything humans have ever built exists beneath that narrow film of gas. Every breath in human history has depended on it remaining stable. And the deeper scientists study Earth's past, the more extraordinary that stability begins to feel. Because this atmosphere was never guaranteed. It survived volcanic infernos, asteroid bombardments, oxygen catastrophes, frozen worlds, mass extinctions, shifting continents, and billions of years of solar radiation. It changed constantly, sometimes violently, yet somehow remained habitable long enough for intelligent life to emerge beneath it. The modern atmosphere feels calm only because humans experience it during a relatively stable moment in Earth's history. Even now, the atmosphere remains active, dynamic, and deeply interconnected with every major system on the planet. Most people imagine the atmosphere as a giant empty space filled with air, but the structure is more layered and delicate than it first appears. Nearly all weather, clouds, and breathable oxygen exist inside the troposphere, the lowest atmospheric layer extending only a few miles above the surface. Above it lies the stratosphere, where the ozone layer absorbs harmful ultraviolet radiation. Higher still, temperatures shift dramatically through thinner and stranger regions, where air becomes increasingly sparse until the atmosphere gradually fades into space itself. There is no sharp edge where Earth suddenly ends and space begins. The atmosphere simply thins until molecules drift farther and farther apart. This gradual fading makes atmospheric loss one of the most fascinating long-term dangers planets face. Even now, tiny amounts of hydrogen and helium continue escaping Earth's gravity into space. The process is slow enough that the atmosphere remains stable over immense timescales. But it is a reminder that atmospheres are not permanent structures. They evolve continuously, and evolution is not always gentle. Throughout Earth's history, atmospheric chemistry repeatedly reshaped climate and life. Carbon dioxide rose and fell, oxygen fluctuated, methane surged and collapsed. Tiny changes in atmospheric composition triggered enormous consequences because the atmosphere controls how heat moves through the planet. Greenhouse gases trap infrared radiation, warming the surface enough for liquid water to exist. Without them, Earth would become a frozen world. Yet too much greenhouse warming pushes climates toward instability. This balance has never been simple. Even now, scientists continue debating the full complexity of Earth's climate systems because oceans, clouds, ice, vegetation, volcanic activity, and atmospheric chemistry constantly influence each other in overlapping feedback loops. Modern climate change adds another chapter to that story. Carbon dioxide Concentrations in the atmosphere have risen significantly since the Industrial Revolution due largely to fossil fuel combustion, deforestation, and industrial activity. Fossil fuels themselves are ancient carbon reservoirs formed partly from prehistoric life buried underground hundreds of millions of years ago. In a strange way, humanity is releasing atmospheric history back into the sky. The scientific consensus remains strong that rising greenhouse gases are warming the planet overall, though exact regional impacts and long-term feedbacks continue to be studied intensely. Temperatures rise unevenly, ice sheets melt, weather patterns shift, oceans absorb heat and carbon dioxide. Some regions face worsening drought, while others experience stronger rainfall or storms. Earth's atmosphere has always changed, but modern observations suggest human activity is now influencing the pace of that change significantly. And what makes this especially unsettling is that Earth's history already demonstrated how sensitive climate systems can become once certain thresholds are crossed. Ancient greenhouse events triggered ocean oxygen loss, ecosystem collapse, and major extinctions. The atmosphere does not need to become completely uninhabitable to destabilize civilizations or ecosystems. Small percentage shifts in atmospheric chemistry can reshape coastlines, rainfall patterns, agriculture, and ocean circulation across the planet. Yet Earth's history also reveals remarkable resilience. Life survived asteroid impacts, volcanic winters, frozen ages, and oxygen crises. Forests returned after extinctions. Oceans recovered after collapses. The atmosphere repeatedly reorganized itself around new conditions, but recovery in geological terms often means millions of years, not decades or centuries. Evolution adapts eventually. Individual species often do not. One of the strangest realizations about Earth's atmosphere is how deeply connected it is to life itself. The oxygen humans breathe comes largely from photosynthetic organisms. Oceans produce enormous portions of that oxygen through microscopic plankton drifting near the surface. Forests regulate moisture, rainfall, and carbon cycling. Soil microbes influence atmospheric chemistry invisibly beneath the ground. Even clouds may be affected, partly by biological particles rising into the air. Earth is not simply a rocky planet with life living on it. The atmosphere and biosphere became intertwined long ago. The planet breathes through cycles involving oceans, forests, geology, and sunlight, all working together. And that connection raises uncomfortable questions about the future. If life helped stabilize the atmosphere over billions of years, what happens when human activity alters those systems rapidly, too? Some scientists worry about tipping points involving ice sheet collapse, ocean circulation changes, methane release from thawing permafrost, or large-scale ecosystem disruptions, too. Others caution that Earth's climate system contains stabilizing feedbacks strong enough to prevent truly catastrophic runaway scenarios under current conditions. The debates are complex and ongoing because climate systems involve enormous uncertainty across long timescales. Yet nearly all researchers agree on one thing. The atmosphere is far more fragile than it appears. The same thin layer protecting life can also shift in ways that reshape civilization itself. And beyond the present lies an even larger truth. Earth's atmosphere will not remain habitable forever. The soot slowly grows brighter over time as hydrogen fusion changes conditions inside its core. Billions of years from now, increasing solar energy will likely intensify evaporation and greenhouse warming on Earth. Oceans may gradually disappear into the atmosphere before water molecules break apart under ultraviolet radiation, allowing hydrogen to escape into space. Over immense stretches of time, Earth could become hotter, drier, and increasingly hostile long before the sun finally expands into a red giant. In the deepest future, the atmosphere itself may vanish or transform completely. This realization changes the way the sky feels. The atmosphere is not permanent. It is temporary stability inside an unstable universe, and yet, despite that fragility, Earth remains astonishingly alive right now. Winds still move heat around the globe. Rain still falls from clouds formed by evaporated oceans. Oxygen still cycles through forests and plankton. The ozone layer still absorbs ultraviolet radiation. The magnetic field still deflects charged particles from the sun. Every system built across billions of years continues operating simultaneously above and around us every second. Most people never think about it while breathing. The air feels invisible, automatic, ordinary. But every breath contains part of Earth's deepest history, oxygen released by ancient biological revolutions, nitrogen stabilized through planetary chemistry, water molecules recycled through oceans, storms, glaciers, rivers, and living cells countless times across geological ages. Some of the atoms entering your lungs tonight may once have drifted through dinosaur bloodstreams, prehistoric forests, volcanic clouds, or ancient seas before humans even existed. The atmosphere connects every era of Earth together invisibly. And perhaps the most humbling part of all is realizing how narrow the conditions for survival truly are. A slightly different orbit, a weaker magnetic field, less volcanic recycling, no moon, a failed oxygen transition, a runaway greenhouse effect, a thinner atmosphere. Any one of these changes might have erased the possibility of complex life long before humanity appeared. Earth's atmosphere was not inevitable. It was the outcome of billions of years of collisions, chemistry, catastrophes, feedback loops, and biological transformations balancing against each other across unimaginable time, which means every quiet night beneath a breathable sky is stranger than it first appears, because above the cities, forests, oceans, and clouds, an impossibly thin atmosphere is still holding back the cold vacuum of space, while carrying the entire history of life within it. Thanks for spending this time exploring the story of Earth's atmosphere with me tonight. 2. If you enjoyed this journey, don't forget to subscribe and leave a comment below telling me what mystery of Earth or space I should explore next.